So today's class is going to be a review class for the last week of content we were doing on the Monday and Tuesday. One of the topics we didn't quite really touch on, in fact at all, would be the sketching of the tan graphs within circular functions. So we looked at how to sketch the sine and cosine, these sort of like wave looking things for sine and cos. We didn't really look at the tan graphs at all. And they are quite different, so I figured it'd be worth dedicating some time towards that. So let's give that a shot. Okay, so just like any other function, the sketching of a circular function has the same sort of coefficients involved in it. So you've got your horizontal translations, your vertical translations, and your dilation factors. All these are changing the look of your overall graph. As for tan, the basic graph of tan with no transformations applied to it looks like this. So you kind of get these little like wobbly lines that are starting from the bottom left and ending at the top right, each separated by these asymptotes, these dotted lines. The way you can sort of think about it is it behaves similar to the cubic, for those who have looked at cubic graphs, where it has like an inflection point in the middle. This is still considered an inflection point. However, when it came to the cubic, it was a stationary point of inflection, which just meant it was a lot like shallower. It had a gradient of 0 there. Whereas this one, we can clearly see it's still sort of ascending at that spot rather than plateauing momentarily. That'll only matter like a long time later. For now, you can kind of just think about this as repeating that shape over and over again over a sequence of asymptotes. That's the gist of it for now. It looks a lot different to the other graphs, and that is because tan is the ratio of sine divided by cos. It's a division of two terms. In fact, that's actually why we get our asymptotes here. So a bit of a thing that's worth considering anytime you see vertical asymptotes. Those will always come about because of a point where the graph is undefined. And a lot of the time it's going to be based on a divide by 0 error. There are other circumstances, like logarithms, for instance, where it's not necessarily a divide by 0 that causes the asymptote, but a lot of times it is. And this case is no exception. So knowing that tan is sine divided by cos, where is it? Where have I written it? Okay, I don't know where I wrote it, but basically, because cos is the denominator of sine divided by cos, we essentially find those asymptotes by figuring out where does cos go to 0 in the unit circle, thus finding where you get those divide by 0 errors. Other key things to notice, it has a range of all real numbers, so without any further restrictions on the domain, it'll shoot from positive to negative infinity, or vice versa, depending on your reflection terms. And without any transformations, what you'll see is that it is symmetrical about the y-axis. So you can see the asymptotes are either side at negative pi over 2 and pi over 2 respectively. Thus giving it a period of pi. That is to say, the pattern repeats with a distance of pi. Any questions so far? Cool. The graph has dilation factors, so that's your multiplication at the very front of the graph. Doesn't matter too much. It doesn't really impact any decision making as far as when you're sketching it by hand. But as you can see, it does technically have an impact on the graph. If the number is bigger, what you'll see is that the line gets steeper, and if the number gets closer to 0, it becomes flatter, and I guess it becomes like more gradual versus less gradual, sudden versus gradual. As far as you actually sketching this, though, you're still just going to draw the basic shape and then just label the key features accordingly. This will only really show up on like a CAS, or if you have to literally describe in your answer, hey, what happens if I change this variable? Which is something that actually comes up quite a bit in math methods, where you'll have the investigation sac specifically I know one of the common threads there is they'll typically ask for you to describe how different variables are changing the graph that you have. And so, even though these fundamentals don't change how we sketch it by hand, you still need to understand what they're doing to the graph for the investigation stack specifically. Then we have the n value, so that's going to be the coefficient on the x specifically. That is also going to be a type of dilation factor in the horizontal direction. Normally, it would have asymptotes at negative pi over 2 to pi over 2. When the 2 is involved there, we're going to see that that shrinks down to negative pi over 4 and positive pi over 4. So essentially halving the distance to pi over 2 rather than pi. The semantics of that specifically you don't have to worry too much about because it will fundamentally just fall down to solving cos equals 0, which is probably, in my opinion, a bit easier to memorize versus the specifics around this. One of the things we talked about was the period, the time in which it takes for the circular function to repeat is actually given by pi with no further dilation factors. The period specifically is calculated by pi divided by n, where n was that term impacting the x. In the other circular functions, it was 2 pi over n. And we've got to figure out, well, hang on a minute, why is there a difference? And once again, it does come down to the fact that tan is the ratio between these two things. And understanding that tells you that the reason why tan is periodic is simply because of its asymptotes. So if you then go and discuss what gives rise to the asymptotes, you'll start realizing that there are 2 spots for any given revolution of the unit circle where you're going to get cos equals 0, right? Cos equals 0 meaning you hit an asymptote, you get a divide by 0 error. And so for every 1 revolution around the unit circle, there are 2 spots where cos will go to 0, cos being the x value here. So x value 0, x value of 0, it occurs twice within the unit circle, which is why you're essentially repeating in half the time that the other circular functions were repeating. Is that fair enough why we're getting pi over n here in this case? Because this is something you'll have to have in your head. This won't be like on a formula sheet, for instance. Cool. Yeah, so if you do need to calculate the period, it'll be pi divided by n. As far as the actual sketching goes, pretty much none of this is going to matter too much. You might use this just for a bit of error checking and self-correcting. Like if you sketch your graph and suddenly you realize, hang on a minute, the period is not what I would expect it to have been, then you can self-correct yourself. But as far as what we'll end up doing to sketch these things, none of this is going to be important for that. It's more so just for the understanding of the fundamental graph. So let's have a look. We're just going to sketch a basic example of it, 3 tan 2x. I'm going to sketch it over the domain from negative pi to pi. Here's the sequence of steps that we're going to follow to achieve that. Let's have a look at how that ends up coming about. So first thing you can do is find the asymptotes. And as we said before, we can do that by solving the cosine component equaling 0. Because tan is sine divided by cos. Asymptotes come from divide by zeros. Cos equals 0, therefore should give us the asymptotes. Just make sure you keep the coefficient, right? So if it's tan 2x, then the cosine portion of that is cos 2x. Basically just rewrite the tan as cos, and then solve for where that would equal 0. That's the gist of it there. It is 2x, so I've done this whole little substitution thing. You don't necessarily have to go through a substitution route though. You can just sort of look on your unit circle, which I should probably bring up actually. Pull that up. There we go. You look on your unit circle for where cos is equal to 0. The good news about that is you're solving the exact same circular function every single time. You know, the location of cos equals 0 isn't going anywhere. So when it comes to sketching tan, it might feel like you're doing a full solve of a circular function, but in reality, these solutions are never going anywhere. It's the exact same one every single time, no matter what the tan says. All you're going to do, all it changes is how many times you go around the unit circle, not where they are. So for instance, this will occur at the pi/2 and the 3pi/2 spot, because again, cos being the x values, where does cos go to 0? Well, it's there and there. And in this case, because we had to sort of fix up our domain a little bit, that dilation factor does effectively double how many solutions you would expect to find. Not only are we going to do the plus minus pi/2, we're also going to do the plus minus 3pi/2. So in both directions there. Because if you just look at this from negative pi to pi, you might expect that you would only go, one half circle this way and one half circle this way, because that's where your pi is, stopping at pi and then going backwards for negative pi. However, that dilation factor of 2 does double this domain, essentially. And you can reveal that with this substitution. I don't think I've really talked much about what's going on with the substitution specifically. Basically, what we're doing is we're subbing in a value for 2x, right? We're just going to say u equals 2x. And because we're now working in terms of u, we've got to replace all these x values with u variables. And so what that ends up meaning is if u is just 2 times x, then it just means you're doubling each of these. So negative pi goes to negative 2 pi, pi goes to 2 pi. That gives you your 2 u solutions. What we're going to do then is just put it back in terms of x, because our graph is in terms of x. Divide everything by 2, and then you get your asymptotes where you expect them in the domain that you've expected to end at. We can see that neither of these values will exceed negative pi or pi. Any questions about finding those asymptotes so far? Okay. Next up, solving for x-intercepts. So for literally any graph, we're always just doing f of x equals 0, right? Letting y equals 0. One of the things you can do to save a bit of time when it's as simple as this, when there's nothing else other than dilation factors, is you'll actually notice that the x-intercepts of the graph are always in the middle of the asymptotes that you found. So if we know that our asymptotes are at plus minus pi/4, plus minus 3 pi/4, then all we've got to do is look in the middle of each of those. So like here's our negative pi/4, here's our positive pi/4. Well, the middle of that's going to be 0. And that should be one of our x-intercepts. Then we had the positive versions of the 3 pi/4 and the pi/4. Middle of that, pi/2. And so once again, that's our other x-intercept. And you'll notice there's also a lot of symmetry in this as well. There's no horizontal translations. In fact, that'd be the only thing that would change it if there were a horizontal translation. In pretty much every case, there's a lot of symmetry involved. So to save time, we're just going to solve using midpoints. You only ever have to worry about this differently if there is a vertical translation, but we'll look at that a bit later. For now, we can hack our way through it by finding midpoints. Basically, you can go straight to there, or if you forget that little tactic, then you can just sort of go back to default, right? Set y equals 0, solve for where tan is equal to 0, so on and so forth. If you do have endpoints, like a restriction on your domain, which in the case of tan, you will always have a restriction because you need to know where to stop doing the repeats, you just sub in the lower and upper bound of your domain into the function, just like you would for any other endpoints. So, we have from negative pi to pi, so we're just going to sub in both negative pi and pi in 2 separate equations to figure out what those would be. In this case, we actually already know what those are. Those are our x-intercepts specifically. So we would only really do that if we didn't know what they already were, which is sometimes the case. Normally when you have like a vertical translation, that could be the case. Or if you have a domain that isn't neat, but that's never going to happen. At least I've never seen it be exceptionally poor. That was one example there. anything to clarify further about that? Because I reckon now we could probably move on to doing a practice one together. Unless there's anything I should clarify first. Cool. Okay. So what I'll do is I'll pop this document in the chat so you guys can follow along with the steps involved. I'll then go over to the book and just sort of copy one of those down for the handwritten notes bit that we do. Do this one. Actually, what did we just do? This one was 3 tan 2x. Okay, 2 tan 3x should be fine. Okay. Y equals 2 and 3x. And we're going to do it over the domain x is an element of 0 to 2 pi. So this will be a little bit different, 0 to 2 pi, rather than having an equidistant domain either side of the y-axis. Okay, I've got that written up. I'll also on the screen share show the steps to follow if you want to look at there, but you do also have a PDF if you prefer to look at that. Who wants to start us off? What are we going to have to do to start sketching this graph?
We have to find the x-intercepts.
Yep, x-intercepts will be one of them. That's fine. How do we get our x-intercepts?
We set the equation to 0.
Yep, we can do that. So y, oh yes, 0 equals 2 tan 3x. Okay. Where do we go from here?
Well, we can divide both sides by 2.
Yep. Getting the circular function on its own and an exact value on the other side. Pull up the tan unit circle if you'd like to refer to that.
It's 0, right?
Yeah.
Oh wait.
So where's tan equal 0? What solutions
yeah,
get us that?
0.
Yep, 0 is one of them.
And 180 pi.
Yep. So typically we'll do things in radians because our domain was in terms of radians, but yeah.
Yep.
We got 0, we got pi.
0 pi and 2 pi. Wait, 2 pi is not included.
Yeah, no, 2 pi is correct. You're allowed to double up on them.
Oh, wait, yeah, it's 3x, so it's triple the domain.
That's it. Yeah, 3x, we're tripling this. So instead of ending at 2 pi, end at 6 pi.
Yeah. So 2 pi, 3 pi.
Yeah.
4 pi.
We can see the pattern.
Pi.
Nice.
Yeah.
5 pi and 6 pi.
So yeah. 6 pi included.
Say again?
Is 6 pi included?
That's a good question. So is 6 pi going to end up being included? Probably not, right? Because these are rounded brackets. So we would expect the 0 and the 6 pi will probably come out. But, yeah, we see that very quickly when we divide back through to get the x back on its own. So, dividing all these by 3, we're going to have our pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, and 6 pi over 3 would have been 2 pi. So again, the 0 and the 2 pi would not be included there. Yeah, so just to recap how we got there, tan equaling 0. Again, we're looking at the values on the unit circle coordinates specifically. So if we have a look at the screen share, it was 0 at the pi. This spot here is 2 pi, and then you just keep going around the unit circle, counting around. How do you know when to sub cos in? How do you know when to sub cos in? Yeah, so that's when you're finding the asymptotes. So we did technically, if we're following like my procedure, you can do this in any order, it's fine. We technically skipped step 1 if we were doing that. The part for cos is for finding asymptotes. This right now is getting our x-intercepts, y equals 0. Yep, so that's our x-intercepts. What else do I need to get? So far, if we're following the guide that I have, we've done step 2, which is finding our x-intercepts. What else? I saw you come off mute, but I don't know if it came through.
Okay, so there are no vertical or horizontal translations, so
yeah,
the y-intercept would be in a feature point. I forgot the name.
the y-intercept will be
the y-intercept will be
like the origin.
Okay. Wait, no. It, it's tangled, so it's going to be 0, right?
Yeah, so it would be 0, because remember, like y-intercept would always be x equals 0, and because it's not inclusive, technically this one won't end up having a y-intercept. But yeah, if that was inclusive, then it would be at the origin. You're right, because if you have a look back at the screen share, no horizontal translation, you can see it's always like the center. All right, it's going to cut through at the origin. But yeah, as far as like what we would need to do as the final thing, we'd probably be getting our asymptotes, right? So that's what step 1 tells us to do. Find the asymptotes by solving cos equals 0. So we're going to do exactly that. Specifically, we're going to make sure it's cos 3x because we want to include any coefficients on the x there. So for our asymptotes, we want to solve where is cos 3x equal to 0. I'll pull up the unit circle to have a look at. Okay. The cos being the x values is going to be here and here on the screen share. The pi over 2 and the 3 pi over 2, at least as far as the first revolution is concerned. We did any more? How would we know if we need more solutions?
We can try and add or subtract the period.
Add or subtract the period? Yes and no. Which period?
The tan graph.
Tan graph. Add and subtract the period of the tan to this. You know, that will work because the cos values are separated by pi. As far as generically speaking, if you're going to do that for a cos, because we basically simplified this down to solving cos now, what you would technically be doing to make it generic for everything would be adding 2 pi to each of the individual set of solutions. And then that would get you any possibility. But in this specific case, cos being 0 is actually fully separated by pi here, so you kind of get away with it a bit. As far as knowing if you need more solutions, it's the same answer as before, right? This dilation factor of, well, technically it's a third, but you know, that coefficient of 3 is going to triple this domain. This domain is still applicable here because both of these functions are being plotted. Well, one of them's being plotted, but this one is inherently based off of the other one. And so yeah, instead of getting the normal 2 solutions that we would expect for 0 to 2 pi, we're now going to triple it out. And we can sort of see from the pattern, we're just adding, yeah, we're adding pi to this over time. So 3, 5, 7, 9, 11, 13. Is that enough actually? 2, 4, 6. Oh, that'll be enough actually. Okay. And then finally, as before, because that's 3x, you want to get it back to x. Pi over 6, 3 pi over 6, which is pi over 2, 5 pi over 6, 7 pi over 6, 9 pi over 6 is 3 pi over 2, and 11 pi over 6. Just double check. Yeah, that's right before 2 pi. So we can see once again all of the solutions that we have here fit nicely between 0 and 2 pi. These are our asymptotes. So it can get a bit confusing if you're not like labeling your steps here as to what's an x-intercept and what's an asymptote, because they both say x, right? Bit of a challenge. So, you know, maybe going out of your way and you're working out to label what's an x-int and what's an asymptote could go a long way to helping. At the same time, it might not matter too much, because when you start sketching a graph, I imagine things would get a bit weird if you try to do one versus the other. Maybe. Could be hard to tell. Anyway. Yeah, we've got everything we need basically. All we got to do now is draw it all up. One thing I would point out here is the reason why I, in the notes, suggest to do the asymptotes first is usually you can use the location of the asymptotes to make solving the x-intercepts a lot easier. Because one of the things we're going to notice is as we start plotting out these asymptotes, is all of the x-intercepts will be in the middle of each of those sets of asymptotes. So I'm going to have pi over 6, pi over 2. I'm going to keep the spacings nice and big so we can put our x-intercepts later. Over 2, 5 pi over 6, pi over 6, pi over 2, and 11 pi over 6. Okay. It's all going to be asymptotes. And then these ones here, so the pi over 3, 2 pi over 3, we'll notice are now going to be midpoints. Pi over 3, 2 pi over 3, pi over 3, 5 pi over 3, and we could put in the 2 pi or the 6 pi over 3, but because it's exclusive, we'll know to leave it an open circle there. Same thing with the 0. Leave it an open circle on the graph to denote that it's non-inclusive, which is probably a reason to make sure you probably still want to label these in your x-intercepts, just so you don't forget that they're actually there. Because you don't want to go back here and be like, oh, I've got to find my endpoints and then resolve that, because that'll take some additional time. But yeah, so a slightly more efficient way of going about things would be do the asymptotes first and then actually just do midpoints from then on, because midpoints are typically a lot easier to calculate than going through a full circular function unit circle thing. As for overall shape, we treat it like the way the cubic works. So positive cubics are always like that. Negative cubics are like that. Same thing with positive tan and negative tan. They work exactly the same way. So we're just going to effectively draw those shapes in between our dotted lines, our asymptotes. This one's got to be cut off early. This one will do something like that. something like that, so on and so forth. Just drawing a sequence of those shapes over and over again. A lot of repetition there, not too many steps. It's more so you'll find that when you're solving it, you just get a lot of numbers to work with. But as far as the actual repetition of things, as soon as you know that, you're just copying that over and over again. Any questions as to how we came to get that? Cool. All right, let's move on to some additional transformation terms. So if we have a look back at the screen share section, reflections. So I actually just brought this up, right? So positive tan is going to normally flow from the bottom left to the top right, just like how the cubic works. If it's negative, it's going to flow from the top left down to the bottom right. One of the interesting things about tan is that it's referred to as an odd function. That is, it has this sort of, even within its little boundary, it has a bit of a symmetry to it. Sometimes it's referred to as like diagonal symmetry, where basically like this part is just a flipped over version of this part. It's kind of like a double reflection. So you would take this, for instance, flip it over to the left and then flip it over up, and you would get the exact same shape up there. That property specifically is referred to as an odd function. And one of the things about odd functions is that reflections in the x-axis are the same as reflections in the, sorry, other way around. No, that was right. Yeah, reflection in the x-axis is the same as a reflection in the y-axis. So essentially, wherever you put this negative, you're going to get the same behavior. And furthermore, if you put double negatives in there, well, you're flipping it twice in the same way. So you're just going to go back to where you started, bottom left to top right. I don't know how common it is to have a negative in the bracket. Let's see. Negative on the outside. Oh, there you go. Yeah, negative on the inside. It's got a precedent. It has shown up at least once. But yeah. I have this written here just in case. This was actually a while ago. One way of thinking about it would be to just sort of, look at where the signs are. All right, if you have both the same sign, positive or both negative, then the overall tan is going to be a negative. Oh, overall tan is going to be positive, sorry, because the double negative cancels. And if they're both positive, well, they're both positive. So you can do a little bit of a sign analysis there, but fundamentally, as long as you understand how your cubics work, just treat it the exact same as the cubics. Lastly is the translation factors. So that's your H and your C, horizontal and vertical. So horizontal translation works the same way for all of the functions, all the way back to quadratics. When you have x minus something, what you're doing is you're shifting everything right by that value. So if we think about like the basic version of tan, it usually had asymptotes at plus minus pi over 2. Those are now going to be shifted both to the right by pi over 2. So the negative pi over 2, which used to be over here, you're now going to have the asymptote at 0. It's shifted over. Same thing with the positive pi over 2. There used to be an asymptote here. Now it's over here. And if you have plus a value, it's just shifting left instead. That's all, really. Now, once again, a bit of a common theme is the horizontal translation, once again, doesn't actually really impact your decision making for this, because it all gets encompassed by when you find your asymptotes by setting cos equals to 0. So it kind of gets, all of this sort of stuff gets solved in the background as you're doing these steps. You don't really have to think and be like, okay, it's a shift right by pi over 2, so I've got to move everything right pi over 2. Really, you just sort of do the steps and then it just works out as a byproduct of following it correctly. This one does impact your solution a little bit, which is the vertical translation. So when you had the vertical translation, firstly, it can be thought of as setting the new inflection point of your tan graph. So it used to wobble exactly on the x-axis in the middle. It still wobbles in the middle, but now it's further up because we've got a +1, right? We're shifting that up by 1. If you had minus, it'll be shifting it down. Worth pointing out, it's not necessarily a key feature for you to label on your graph. It's more so there, so you want to make sure the graph doesn't look like shit. You want to draw the wobbles in roughly the same spots on all of your iterations. So it might be worth doing like a little dotted line there, just to make sure you're drawing those in the right spot. Not required, though. It's more so just for demonstration for you guys to see that that's what's actually happening. So one of the key things to watch out for here is, because that's now shifted up, your x-intercepts no longer occur in the middle anymore. They're slightly offset. They used to occur in the middle of the asymptotes. Now they're, in this case, a little bit to the left. Now we are forced to find them by setting y = 0. We don't really have another choice. Same for the x-intercept. Sorry, the y-intercept actually. Although without horizontal translations, the y-intercept will usually just be whatever your vertical translation is. So, you know, it's +1 here, so it's 1 here. If you get a horizontal and a vertical, you just sort of got to go back to the worst case scenario, which is setting your x and y equal to 0. So yeah, we updated ever so slightly. We'll now notice that when it comes to finding the axes-intercepts, we don't have that luxury of midpoints anymore. Let's see how it ends up working. This is a nasty one, dear God. Okay, I've put everything in there just because why not? So we got our reflection, we got a couple of dilations, horizontal translation, and a vertical translation. So you got everything in there. So if we can do this one, we can definitely do all of the ones in the book and the exam. One of the first steps we want to follow for any of these complicated things is to just rewrite it in a way where we can see all the key features that we're looking for. Specifically for tan, it's not going to matter too much, but it's a good habit to have anyway. The good habit, of course, being making sure we take any coefficients off of the x, because that'll reveal the true horizontal translation term of pi/3 rather than the pi here. This kind of hides it. From there, we can find our asymptotes again by essentially rewriting this as cos instead of tan, and then solving the cos version of that. There's a whole bunch of complications going on in here. It makes it kind of difficult to know what the real domain is going to be. Like, you know, we saw our little cheat before, which was if there was a 3 there, it means triple the domain. But because we have this horizontal translation as well, yes, we're tripling the size of the domain, but we're also offsetting it ever so slightly to where even if we do get triple the solutions we're expecting, we might not be getting them in the right spot. And so this is where I would definitely recommend doing a substitution approach. What does that look like? Well, again, basically take whatever's on the inside of the brackets that you have, let it equal to u, or whatever variable you want. That's going to rewrite it. Instead of saying cos of all this equals 0, it's now just cos of u equals that. Nice and simple. But because we're using u instead of x, we need to figure out how to rewrite our domain. The way that works is with a substitution into the equation we just created. U is the same thing as 3 times x plus pi/3. So every one of these x values we shove in the x spot, and whatever comes out is a u value for that equivalent, the equivalent u value. So when you shove in negative pi/2, weirdly enough, you do actually just get right back to negative pi/2 for this one. It's a bit strange. But for pi/2, you don't quite get that. This one ends up being 5pi/2. And that gives you a new effective domain there to work out. So we now just got to figure out where does cos go to 0 within that. This did end up turning into actually quite of a nice domain because it's all pi/2 type. And if we remember from before, cos goes to 0 again at the exact same spots. pi/2, 3pi/2, 5pi/2, 7, 9, you know, all the odd pi/2s basically. And so yeah, we just do that in both the positive and negative direction as far as we need to. So plus minus pi over 2, then 3 pi over 2, then 5 pi over 2. And well, sure enough, that's how we're going to end up stopping. Now instead of having like just a 3x there, we've still got to have the full thing of what u actually is. It is all of this. So instead of having u equals all of these things, we now have that equals all of these things. From there, it's just basic algebra, right? Start by unwrapping the brackets by dividing everything by 3. That'll give you denominators of 6 instead of denominators of 2. And then you subtract pi over 3 from all these values. That one's a bit harder. Only looks like a lot because I've got everything on the same page at the same time. But all you're doing is saying, okay, what's minus pi over 6 minus pi over 3? Well, if we follow that one specifically, make sure you just get your same denominator. And then, yeah, complete your subtraction for all of those. And when you look at your final set of solutions, you'll see that they'll all fit within the domain that we want. Starting at negative pi over 2, ending at pi over 2. And sure enough, that's what we wanted to have happen. There are a few steps. So all that was just finding the asymptotes. To recap, you just convert that into cos, figure out where cos goes to 0 within that new effective domain, and then just make sure you're dividing everything back down to fit back in. We're sort of undoing our substitution there. That's going to be the hardest part out of all of them. So I'll just pause there. Is there any questions as to how that one came to be? Cool. Okay. Part 3, super easy. What's your vertical translation? That'll tell you the y value of your inflection point. The vertical translation is always the plus on the outside. So vertical translation is 2. The inflection point will occur at y equals 2. That's this thing, the blue dotted line, where it wobbles every single time. Nice and easy. Then from there, identifying the shape of the graph. So we've got one reflection term in there. One reflection means instead of going from bottom left to top right, it'll now go from top left to bottom right. Top left to bottom right. Cool. And then for axis intercepts, like we've seen before for every other graph ever, y-intercept, you let x equal 0, x-intercept, you let y equal 0. As for the specifics, for x equals 0, that'll simplify down to having tan of pi here. So we go to our unit circle, which you guys do need to eventually have memorized if you don't already. Tan at pi is 0, and so sure enough, that whole thing is going to now disappear, leaving you with just plus 2. That's your y-intercept. Which, yeah, that's actually kind of cool, because even though we did have a translation involved, the y-intercept was still, equal to the vertical translation. That's interesting. Maybe it was just lucky. Anyway, the y equals 0 version's a bit harder, because now you have to do the opposite, which is solving for whether values are equal to a thing. So you get 0 equals this big nastiness. First step, rearrange to make sure the circular function is on its own. So subtracting 2 from both sides and then dividing by -2. That'll give you one of the exact values. So tan equals 1. That's going to be that and that. And yeah, again, we can do our substitution approach to make life a little bit easier, or at least look a little bit easier. Good news is when it comes to fixing the domain, we've technically already done it, right? The domain of the cos should be exactly the same as the domain of the tan, because we're still sketching over the same domain. So we can just sort of borrow that from earlier. So no further effort actually has to be done here. You just do shove in the u where it should be, and then borrow that domain from earlier. Then, as I said, just look for where tan is equal to 1. That's going to be at the pi over 4 and the 5 pi over 4 spots, respectively. Pi over 4, 5 pi over 4. Just keeping in mind, of course, this does go for more than one revolution. right? One revolution of the unit circle is 0 to 2 pi. That number 5 pi over 2 is a little bit bigger than 2 pi. So 5 pi over 2 will end up actually being in this relative spot when you count around a bunch of times. So we will get another copy of this spot, which I believe is the 5 pi over 4. Oh, sorry, we already did that one, 9 pi over 4. Yep, that'll give us all our solutions. And then once again, the same thing as before. Shove back in what the x-related stuff was, and then, well, simplify. Dividing everything by 3 gets you your denominators of 12 rather than 4. Subtracting pi over 3, you want to convert that to same denominator, and then complete your subtraction. Once again, sanity check, make sure everything is between our domain that we want, which was negative pi over 2 to pi over 2. So, yep, that's smaller than negative pi over 2, and that's bigger than negative pi over 2, and that's smaller than pi over 2, just barely. If you do need to find endpoints, sub them in specifically. In this case, our pi over 2 and negative pi over 2 were actually asymptotes. So we already know what those key features relate to. We don't have to then resolve them to see what happens. And yeah, we got all our key features. So we found our vertical asymptotes, that's that. We know where our inflection point should be, that's that. We know the overall graph shape because it's a net negative tan. And then yeah, the axis intercepts, both our y and our x stuff. Typically you'll dot out the asymptotes first, and then then you do the x-intercepts after that, then probably draw your curve through that. Alternatively, you can do your asymptotes, draw the curve, and then wherever your curve goes through, you just put a tick on them and label it that way. But that's a super minor nitpick for neatness' sake, because unless you have steady hands, you may or may not miss your mark, but I'm sure that'll be fine. Yeah, that's as complicated as tan graphs are going to get. So if you're happy enough with how that one works, then you'll be happy enough with how all of them work. Granted, of course, it's probably going to take a few practices to get there. So if you have a look at what's in the actual... Well, actually, some of them are a bit crazy. What's in the exam is far less. Usually is. Because we looked at this earlier in, what was it? Was it lesson 2 or lesson 1? One of them, where we had a look at the actual, my exam paper actually, from when I graduated, and it had like a vertical translation in it, and that was it. So we're going above and beyond just because your SACs may or may not be harder, but I can say for certain the exams, they pull punches a little bit, because there's a lot involved in sketching these graphs. That's it for the lecture portion. Is there any questions as to how this has worked? We'll do a practice. I'll grab a screenshot of this as well for the chat if you want to follow these steps for when we do a practice. Anything I should clarify first? Cool. Okay. Let's see a good one. Yeah, let's give 3A a shot. It's got a horizontal and we're not going to have time for 2 examples, I don't think, so I'm just going to add a vertical translation to this. Let's see. Y equals 2 tan x plus pi over 4. Well, actually, I need to be careful with what I choose as a vertical translation, because it may or may not work. I think plus 2 should work. Because there's only a certain set of values that exist on the unit circle, so I've got to make sure I pick the right, well, one that would work out. I'm also going to adjust the domain a bit. We did a 0 to 2 pi last time. Let's do a negative pi over 2. Let's do negative pi to pi. Hopefully it's not too small. I guess we'll find out shortly. Alright, that one's written down. I'll also have the steps to follow should you want to revise that on the screen share. Who wants to take a stab at it first? Step 1, rearranging into the general form. We don't necessarily have to do that here because everything is clearly visible to us. There's no like coefficients to be taken out. We can see all the translation and dilation terms. Not that it matters too much. It's more so just a good practice thing. That would lead us to step 2 then, which would be finding the asymptotes by solving cosine equals 0. So how are we going to do that? To reiterate there, basically when it came to finding the asymptotes, you take the circular function portion and essentially just rewrite it as cos and then make that equal to 0. As for the actual solution of that, we typically would be using a substitution approach. So basically what that would look like is you take what's on the inside here and let it equal to some letter. I just default to u. That's going to give us u equals x plus pi over 4. That way, things are a bit nicer, because now we just need to figure out where does cos equal 0. And cos equals 0, the exact same spots that it did before. If you have a look back on the screen share, I'll have that highlighted there. It's the pi over 2 and the 3 pi over 2 spots. Both the plus minuses of those actually, because it goes in both the positive and the negative direction. In this case, we want to do from negative pi to pi. So I'm going to have plus minus pi over 2, plus minus 3 pi over 2. That's probably enough. We can always find out exactly how many we need by fixing up our domain. In fact, this will probably be too many. So does anyone remember how we fix up this x domain to be in terms of u? Yeah, okay. These are probably one of the harder things to work on. Because we're working in terms of u, and we have an equation that tells us how to get from, or what the relationship is between u and x, we end up using this to help convert between one or the other. So this is an x domain. All of these x values are going to go in the x spot of the u equation. So if we do that in 2 separate steps, we got u equals negative pi plus pi over 4. That'll be fixing up this one here specifically. That's going to be u equals negative 4 pi on 4 plus pi on 4, getting same denominators so we can do that addition properly. And that's going to be u equals negative 3 pi on 4. So that'll be the new lower bound. New upper bound, same thing. So again, it's going to be x plus pi over 4, where in this case x is going to be the pi. That's our upper bound. Pi plus pi over 4. U equals 4 pi on 4 plus pi on 4. U equals 5 pi on 4. that's what the new domain ends up looking like. So this lower bound is actually a little bit further to the right, and this upper bound is also a little bit further to the right, which should make sense, right? We're adding pi over 4 to both of those. So if we have a look at what we created, negative pi over 2, that'll fit, but negative 3 pi over 2 is too big. Right, so if we look at like on the unit circle, that's a great circle, dear God. If we look on a slightly better circle, this would be negative pi over 2 here. This would be negative pi. That would be negative 3 pi on 2. Negative 3 pi over 4 would be like, well, sorry, it'd actually be dead center there. Negative 3 pi on 4. So we will get the negative pi over 2, but we won't get the negative 3 pi over 2 on that. Similarly, if we count around the other way, this will end at 5 pi over 4, but it's fundamentally still the same thing. So this will be pi over 2, pi, 3 pi over 2, and 5 pi over 4 would be just after pi. So we'll include this, but not that. So in total, the ones that we do actually end up keeping are going to be the negative pi over 2 and the positive pi over 2. No, yeah, 3 pi over 2 doesn't belong to any of them. So it's just plus minus pi over 2. We ended up going a bit too far. Fair enough how we're able to truncate that. Okay. That's our, what's this one again? This is getting our asymptotes for cos 0. So that's our asymptotes in terms of u. We do want them back in terms of x though. So we rewrite what u is in terms of x, and we make that equal to our possibilities. Do our simplification. So I'm going to have the negative version minus pi over 4 and the positive version minus pi over 4. That's going to give you negative 3 pi over 4. I'm just sort of skipping steps a little bit, the simplification steps to get there. And then this will be pi over 4. Those are our asymptotes. But I guess asymptotes, if we have a look back at the screen share, the next step would be getting our vertical translation to get our inflection point. Vertical translation is +2, so that's going to be a y equals 2 inflection point. Nice and easy. Shape of the graph, it was net positive, I believe. Yeah, both positive coefficients, so it's going to go something like that, bottom left to top right. Axis intercepts, let y equal 0, let x equal 0. Let's quickly do that. Okay. 0 equals 2 tan x plus pi on 4 plus 2. Subtract 2, divide by 2, gets you negative 1. Pi on 4. Do our simplification again. So tan of u equals negative 1. And we can use that domain from earlier. Negative 3 pi over 4 to 5 pi over 4. Minus 3 pi over 4, 5 pi over 4. Where does tan go to negative 1? If you have a look at the screen share, I'll pull up the tan unit circle. Negative 1 is at the 3 pi over 4 spot and the 7 pi over 4 spot. Which means we're going to have the plus minus of that, so plus minus 3 pi over 4. 7 pi over 4 is going to be too big for this. getting that back in terms of x plus pi over 4 equals plus minus 3 pi over 4. I have just noticed we've hit time. If you guys need to go somewhere, feel free to hop off. I'm not going to hold you captive unless you want to stick around. We're just going to wrap this up. Shouldn't be too much longer anyway. Simplify that down. That's going to be, so the negative is now going to be negative pi, and then this one's going to be, so positive, oh, yeah. No, sorry, that was the wrong way around. That should be pi over 2. Those are our intercepts. Then we just wrap it up. So we had asymptotes, negative 3 pi over 4 and pi over 4. The intercepts at minus pi and pi over 2. Endpoint pi. Y equals 2 for our inflection point. And it's going to do like a bottom left to top right sort of thing going on. Which means I stuffed up somewhere along the way. There should definitely be an intercept in here. That's what I get for speeding through it, I suppose. Where did I miss it? Negative 3 pi over 4 minus pi over 4 is negative pi, that's that. Positive 3 pi over 4 minus pi over 4 gets you pi over 2. Should have a little bit of something going on like that, but we don't. What do I do? Oh well. There's better solutions to this on the actual document. I don't think I'll solve it or find the issue in a meaningful amount of time. But the more important thing there is making sure you're getting the steps right. You're going to have algebraic issues, even when you've been doing this for God knows how many times. The steps are all there. You've got a full solution to follow there. If there's anything further to clarify, feel free to ask any questions. I'll stick around for a little bit. Otherwise, I'll see you in the next week. You guys have questions, or are we just AFK? Uh-oh. I've bored everyone to tears. Alright, if you have any questions, let me know. I think you all have my number. If not, you have my school DM chat thing. I'll leave you to it. Take care.